Few words about me. I'm a distributed system engineer. I wrote a paper on Kaspaxes. Currently I work at Vectorized, and before that I was working at Microsoft on Cosmos DB, where I tested consistency. I like to measure performance, but I can't decide what I like more, P99 or P0, because P99 is like measuring car performance in a busy city with a lot of pedestrians, stop lights and speed limitations. And P0 is like taking this car on the tarmac, and every data that we get, it represents the pure performance without any additional noise. And if we get data which are not physical possible, for example, when our car goes faster than speed of light, we have a clear signal that something is wrong with the system. When I don't work on distributed system, when I don't read papers, I like surfing. Surfing is a pure joy, so if you don't surf, you should start. Today we're gonna talk about this chart, and I guess you already know what this is about. On the x-axis we have concurrency, and the data that it shows, it's kind of a stabilized at some levels. So one chart is close to 200, another is 800. So I think you know what is it. It's a throughput. What else it could be? Latency only increase with the growth of the concurrency. But what is surprising about this chart is that we have a system with transactions performing faster than a system without transactions. And if you have told me this several years ago, I had thinking that you are joking, because everybody knows that transactions are just slow. There is academic papers dedicated to this topic, and people on Stack Overflow knows this. People on Hacker News always mention this. So it just can't be true. First, we need to understand what makes transactions slow. And once we're here, we will understand why sometimes they might be faster. So I'll start with a simple example. Let's forget all of these hard distributed topics and focus on the topic which is familiar to us from the college. It's a sorting algorithm. Here we have two sets. Set A is just all functions from list to list, and set B is all sorting functions from list to list. And obviously all sorting functions are just functions from list to list. So we have B as a subset of A. And this is enough to say something about performance of these functions. Simple maths shows us that performance of sorting functions can be faster than performance of just all of the functions. And it's easy to see. The minimum element is B, is also an element is A. And it might be either minimal in A, or there exists another element is A which is less than it. So we have this very simple equation. And on the casual level, it basically means that the more work we do, the worse performance we have. We will see how we can hack these situations, because everybody knows that Sorting functions has n logarithm n complexity, but there is some magical sorting algorithm which can perform better than this. So there is a couple of examples. We have a radix sort, which has linear complexity, and we have a counting sort, which also has linear complexity, but with much better constant. So how they are doing this? Maybe we can do the same with the transactions. So let's figure this out. Just like with our previous examples, let's focus on the sets. We have two sets. One is set A, which is all sorting functions from list of bytes to list of bytes, and we have all sorting functions from list of integers to list of integers. And if we have a function which can sort integers, it also sorts bytes. So we have this kind of an inverted relationship. Inverted is because byte is an integer. Byte is a subset of integers. But when we focus on the functions, we have this inversion. It's called contravariance. And we have a function of int is a subset of a function of bytes. And once we have this relationship, we can use the familiar trick, and we can see that performance of the sorting functions of bytes can be better than performance of a regular, so of all of the sorting functions. So in the casual sense, it means that specialized system has better performance than non-specialized system, and the same works with the transactions. Maybe we can find situations when the transactions may perform better. So in our case, it's bulk insert. So what we gonna try? We try to insert as many messages as many messages as fast as possible to our system. So this is a pseudocode of a Kafka client which interacts with either Kafka or Redpanda. Usually, Kafka clients are asynchronous, so it means that when we want to send a message to the system, we are not blocked, and this API returns a future, or in other languages it's called a promise. So we can insert a lot of messages, and then at some point later we can actually wait until they are executed. So let's take a look on what's happening inside of the system when we execute this code. Kafka clients are smart. They don't call so kind of they have its own logic, and they try to limit the throughput. So when we execute a lot of send requests, they actually in the beginning are in the pending state, and with time the Kafka clients takes the first several requests and executes them, and then it waits until they execute it. They got executed at some point of time, and when one request get executed, Kafka clients schedule the next message batch. So at each point of time there is a limited amount of in-flight requests, and eventually they all get executed. All of this process looks like a like a progress bar. let's try estimate latency latency y of these kinds of workloads. Since we limit the number of in-flight requests, this latency is linear to the total number of messages that we want to write. And each step in this procedure depends on the replication protocol, on the disk I/O, on the distance between the client and the cluster, and on the intercluster communication. So that was kind of a naive approach to insert a lot of messages to the system. Now let's take a look on the transactional example. So this is a pseudocode of the transaction operation. We begin a transaction, then execute a lot of the send requests, and then we commit transactions. But if we take a look on the protocol level, for example, with TCP DAMP, then we may notice that this first call begin transaction actually doesn't reach the server. It's just a local call to the library to indicate that we're about to start a new transactions. But first send request is actually does this additional magic, which talks with the coordinator and adds the topic to the current ongoing transactions, and then all of the follow-up sends are just going and write the data bypassing the coordinator. So in this example, I decide, okay, let's just forget about this begin transactions and write only all of the RPC calls that we have in this workload. So this is it. All of the send logic that I've described lately, remember the progress bar, stays the same, but we introduce two additional remote procedure calls. So when we look at the latency, it becomes this. So we again have a linear kind of complexity, linear number of steps. Each step depends on the replication protocol, disk I/O, client cluster distance, and intercluster distance. But we also add several additional RPCs, add topic to transactions, and commit. In order to understand what Redpanda, how Redpanda optimized this example, let's first focus on the on the Kafka protocol, and then see what Redpanda has modified to have this performance gains. So this is a add topic to the transactional workflow. It's a sequence diagram. So we have a client, and the client sends a request to the coordinator. Then coordinator updates its internal transactional state, replicates it to the internal topic, to its replication group, and then confirms the request to the client. So basically it's just kind of one client cluster hope, and then several, one, in the happy case, it's a one intercluster hope to replicate the coordinator state. So now take a look on the commit procedure. So we have, again, we have a coordinator, and we have a topic. User sends a commit request to the coordinator. Coordinator marks that we are going to commit this transaction, and then it's immediately acknowledge request to the client. So it looks a little bit dangerous, because it looks like we haven't committed anything, but we already confirmed the operation to the client. But this called strong eventual consistency, and it's totally fine. It doesn't cause any anomalies, because we persisted the state of the transactions. And after we confirm a request to the client, we execute this cleanup procedure, which communicates with the existing topics, commit the transactions on their part, and then we eventually mark these transactions as committed. So this was the Kafka way of doing this. So let's take a look which optimizations Redpanda does. So first of all, we decided, okay, let's send be eventually consistent. We don't want to pay for the replication, but eventual consistency is dangerous. It's prone to anomalies, and in order to get rid of these anomalies during the commit phase, we actually check that all of the send data were fully replicated. So first we can pretend that we're eventually consistent, but at some point of time we wait that everything is done. It's something like a memory barrier in a regular languages memory model. And this additional step to validate that all send are fully replicated introduce additional intercluster calls, but we don't want to pay price of this additional intercluster calls, so we use CockroachDB optimizations called the parallel commits. So all of the additional stuff happens in parallel, so overall the latency isn't increased. Let's take a look on the changes in the protocol. This is a add topic to partition call. We can see that there is one additional communication round. Once coordinator receives a request from the client, it communicates with topic and asks this topic who's your leader and what is the version, and then it persists this information in the transactional objects and confirms the request to the client. Now let's take a look on the commit phase. So commit phase is also, we added one phase or one round of communication. So we have a client which sends a commit message to the coordinator. Then the coordinator reaches out to all of the transactional topic which participates in the transactions, and basically it's asks them, please finish replicating all of this eventually consistent return messages if the leader and its version hasn't changed. So when it's true and when it's sends a request to the coordinator knows that all of the data was fully replicated, and from this moment it executes the regular commit procedure. We can see that we introduce this additional communication and additional write, this prepared, which is necessary to make sure that the replication is finished, and it happens sequentially with the marking transaction object as committing. So we don't want to pay price for this communication. So in the real world, this thing is a little bit more complicated. We're using parallel commits optimization, and it's all happens simultaneously. So let's take a look on the latency again. Remember this breakdown. Now we get read from the replication protocol, we get read from the disk I/O, we get read from the intercluster communication. For the sent data, there is only client cluster. There is only one hop from the client to the cluster. And of course, there is a still add topic to the transactions and the commit phase. And all of these optimizations, they explains why we have these charts, why the system with transactions performs better than without transactions. So once again, we instead of executing all of this sends request one by one in isolation, we use transactions to scope a unit of work, and then we optimize this unit of work as a whole instead of optimizing each its internal step. But I want to be honest with you. This is we compare a system with transactions with a system without transactions, but with the default settings. If we optimize settings with for the maximum of the throughput, we will get this chart. So non-transactional performance gets better, but it's still worse than the transactional thing. I think you guessed. Okay, you have demonstrated that this particular one example of transactions is working fast. But what's about the regular stuff? What's about streaming? So this is a streaming data. Kind of naive streaming without transactions, it gives us 0.6 milliseconds, and with the transactions it's 2.8. Transactions are 4 times slower than the system without transactions, but this 4 times it's a really good result. It's best that exists in the streaming right now. A couple of the takeaway: if you design a data-intensive application, avoid disk I/O to make it fast. Embrace the limitations that you have. One person's limitations is another person's specializations. So maybe it's an opportunity to make the system faster. Be optimistic. Sometimes adding a slack in the system can make it better and more performant, just like we did with relaxing consistency of the send request. And look around. This parallel commit optimization that I was mentioning, it was invented just a couple of years ago. So this system won't be possible even 5 years ago. So maybe somebody right now working on improving solution to your problem. Thank you. I was happy presenting this at the P99 conference. If you have any questions, I will answer them in the chat. Thank you.